Good evening, everyone. So I would like to thank the organizer for providing me the opportunity to present my work in front of you all. So the topic of my presentation is exploring the magnetic coupling of the solar atmosphere using 3-minute slow magnetoacoustic waves. So in this, I will be telling you that why magnetic coupling of the solar atmosphere is very important to study or to explore, and why we are using 3-minute slow magnetoacoustic wave to explore this this magnetic coupling of the solar atmosphere. So we are very well aware of the coronal heating problem, as it is one of the longest standing problem in the solar physics. So coronal heating problem is basically that the temperature of the atmosphere increases as we move away from the heat source. So this is the coronal heating problem. Now, when we see this wave plot in which we can see the temperature variation along the solar atmosphere, we see that yeah. So is my pointer visible?
Yes.
Okay. So here we see that at the photospheric height, the temperature starts to decrease, which is expected that because as we are moving away from the source, the temperature should decrease, and it decreases to about from 6,000 at the photosphere to about 4,400 Kelvin. At the temperature minimum height. Now, from this height, the temperature starts to increase, and in the chromosphere, it reaches roughly around 10,000 Kelvin. Then from the chromosphere, it shoots up to about 1,000,000 degree Kelvin in the corona in just a small height. So this layer is known as the transition region, where there is a sudden change in the density and temperature. So here we can see that the temperature of the solar atmosphere starts rising from the chromosphere itself. So the lower atmosphere is playing a very major role in the heating of the solar corona. So that is why we need to explore the coupling of the solar atmosphere, because the corona is not energetically isolated. Since the chromosphere is playing a major role, so we should couple the whole solar atmosphere and then try to explore the reason of the heating. So the coronal heating problem is very well described in a few of these review articles. Now, the coronal heating to explore the coronal heating problem, there are various proposed mechanisms, and two of the most promised heating mechanisms are the reconnection mechanism and the wave heating mechanism. So I will be focusing now on the wave heating mechanism. The wave heating mechanism, so this is a schematic diagram of how the waves are generated, how they are propagated in these loop kind of structures. So when we say the wave heating mechanism, we can categorize or divide it into 3 parts. First is the generation of these waves. Now, when we see these loop kind of structures which are coming out from the photosphere, so there is convection motion happening at the below the photosphere, due to which granulation patterns are visible on the photosphere. Now, these granulation patterns shakes these flux tubes and the waves are generated. But we can notice that the cross-section area of the loop shrinks, and it's very small at the photosphere. So observationally, we cannot detect observationally we cannot detect the generation of these waves. Then, since the waves are generated, now they are propagating. Now the propagation of these, now when these waves are propagating from the photosphere, they encounter a steep change in density and temperature at the chromospheric and the transition region height, due to which a certain fraction of the wave gets reflected back to the solar atmosphere, and only a small portion is able to reach the corona. So the propagation of then while these waves are propagating, they show signature of damping as well. Now, the observation of the actual damping of these waves from photosphere to the corona is still not possible. Now, why it is not possible, I will be showing that in my upcoming slides. So the wave, so there are few review articles in which we can these wave hitting mechanism is explained very well. These are the few review articles. So here we can see that these waves are propagating in these loop kind of structure. Now, which are basically the magnetic flux tubes. So we selected so to study these waves, we selected a region where the magnetic field is high so that we can clearly see these loop kind of structures. So for that, we will study these loops in the sunspot umbra. So to study these waves in the sunspot umbra, let's see what previously have been studied about these waves in the umbra. So this is a photo of a beautiful fan loop structure. So this fan loop structure is visible in the corona, trace 171 angstrom pass band. Now, in which we can clearly see these loop kind of structures. And in these loops are rooted in the sunspot umbra, which display longitudinal compressive waves in the form of intensity perturbation when they are propagating along these coronal loops. Now, to determine the characteristics of these waves, we make a time distance plot along these loops. And from here, we see bright and dark ridges. And from determining the slope of one of the ridge, we can determine the speed of these waves, which is around 122 kilometers per second, which is less than the speed of sound. So we call them as slow magnetoacoustic wave. And from this time distance plot itself, we can determine the period of these waves, which came around 3 minutes. So these 3-minute slow magnetoacoustic wave along the loops are very well studied. Now, from the corona, when we move to the chromosphere, we see 3-minute oscillations are again present in the form of umbral flashes and umbral waves. So on the photosphere, we can see this is an umbral image. So these bright regions are the umbral flashes. So this is a hand-drawn image of the umbra, in which we can see that umbral the motion of these umbral flashes. So these are again 3-minute oscillation. So on the chromosphere, again we have 3-minute oscillation. Now as we move lower in the solar atmosphere, we have the photosphere. So at the photosphere, the 5-minute oscillation are dominating compared to the 3-minute oscillations. So the 3-minute are weaker at the photosphere. So so here in this image, we can this plot this is the FFT power spectrum of the Doppler velocity. So here we can see that this solid line is for the photosphere, where it is 3 millihertz. So 3 millihertz is approximately 5 minutes, and this is approximately 5. And this is for the upper height. So the frequency is around 5 millihertz, so which is approximately 3 minutes. So here we can see a shift in the period when we are moving from the photosphere to the upper layer. Now, why does this happen? This happens because of the acoustic cutoff. So So due to the acoustic cutoff, which is so the acoustic cutoff frequency is around 4 minutes. So all the periods which are below this frequency are allowed to propagate up into the solar atmosphere, and all the periods which are above this 4 minutes are cut off and they are reflected back. Apart from 3 minutes and 5 minutes, there exists 1.4 minute also in the umbra, which have been detected by Wang et al. In 2018. So in the umbra there are various oscillations or various waves present. Now to study these waves, we have selected a sunspot. So in this, this is a fan loop structure in which we have traced 8 fan loops. So this contour here represents the umbra. So these fan loops are coming out from the umbra. I will be showing. We did analysis over all the 8 loops, but for this presentation, I will be showing you the result for loop number 8 as a representative example. Now, along this loop number 6, we make a time distance plot. So this is the time distance plot where again we see bright and dark ridges. Now we can determine the slope of these one of the ridge and determine the speed. So this time distance, the slope of this time distance plot gives us the speed of these waves, which came around 6 km per second, which is less than the speed of sound in corona. So that is why we know that these are slow magnetoacoustic waves, and we can determine the period of these waves as well. So these are 3. So in the corona, 3 minute slow magnetoacoustic waves are propagating along these loops. When we move to the low, we can clearly see the loops in the corona. But when we move to the lower atmosphere and we want to trace these loops, what we see is that the coronal loops are not visible in the lower atmosphere. So in the corona, the loops are clearly visible. And as we move to the lower height, that is the transition region, the loops are not visible. And when we move to the chromospheric height, we can see that umbral structures. And when we move to the temperature minimum, we can see the umbra and penumbra. And at the photosphere, we can clearly see the distinction between the umbra and penumbra. So this structure itself shows that why the coupling of the solar atmosphere is so difficult, because the solar atmosphere looks very different when we try to probe the different layers of the solar atmosphere. So if we want to see that from where this 3 minute is coming in the corona, we need to trace these loops into the lower solar atmosphere, which is a big challenge because we cannot visually see them. So to trace these loops in the lower solar atmosphere, we devise a technique. So for that we know that from where this loop in the corona is, we can see. So this asterisk symbol represents the loop foot point in the corona. So basically this is the coronal foot point. From we will determine the light curve at this location, and then we will use this 5x5 arc-second box in the lower atmosphere to detect the loop location in the lower atmosphere. So for loop tracing, so as I said that we will determine the light curve at the coronal foot point. So this is the original light curve, and this blue line, overplotted line, is the 16 minute background, smooth background. And when we subtract this background from this original light curve, we get this detrended light curve. So we will be using this retrended light curve to to determine. This is the same 5 cross 5 arc second box. We determine the light curve in AIA 304, which represents the transition region. We determine the light curve at each pixel in this 5 cross 5 arc second box and correlated it, determine the maximum correlation coefficient and make this correlation image. Now in this correlation image, we can see a bright patch kind of structure. Now in this patch, we can see this red circle. So this red circle is basically the loop cross-section of the loop in the corona, which we can see in the coronal images. And this contour is depicts the loop cross-section at the transition region. So here and the center of this loop represents the loop location at that atmospheric height. So now we have determined the loop location in the transition region. Now we use the similar analysis to determine the loop location at each atmospheric height. So this is, we determine the loop location and cross section in IRIS 2796, which depicts the chromosphere. Then in AIA 1700, which depicts the transition region, and then the HMI continuum, which is the photosphere. Now, when we see these contours, we can see that this loop contour is shrinking as we are moving into the solar atmosphere. So at the photosphere, we due to the due to the spatial resolution limitation, we are stuck only at 1 pixel. So so basically this shows that the loop is shrinking. So loop is shrinking as we are moving into the solar atmosphere. So this is how the cross section is varying from the photosphere to the corona. So this basically shows the expansion of the loop as we are moving up with the height. So this is so why does this happen? This happens to balance the horizontal pressure. So this loop expansion is basically depicting the flux tube expansion is in accordance with the flux tube expansion theory. So this is the first indirect observational evidence of the loop expansion with height. And this is a technique which we have developed to trace the loop from the corona to the photosphere, which were previously we cannot detect these loop and their cross section in the lower atmosphere. Now now further what we did, we have the location of the loop at each atmospheric height. So we determined the so from the original light curve, we made a Fourier power spectrum. Now in this Fourier power spectrum, we can clearly see the 3-minute is present at each atmospheric height, while the 5-minute is only present at the photosphere. So we applied a band pass filter over this band and determined a filtered light curve. So this is the filtered light curve, which shows clean wave packets. So these are very clean oscillations, and these are basically wave packets. So it is showing a beat kind of a pattern. So this is basically the amplitude modulation. So this blue line here is the amplitude modulation, or the envelope of these beats. So then we determined the we applied Fourier power spectrum over these amplitude modulation and determined the modulation periods. We did this. We determined the amplitude modulation from the wavelet as well. So black line is from the wavelet, what we determined from the wavelet analysis, and blue is from this maxima minima method. So here we can clearly see that a common modulation period is present at each atmospheric height, shown by these shaded regions. So apart from this, we use cross correlation method also to determine whether these amplitude modulation are correlated at each atmospheric or not. We found a significant amount of correlation between these amplitude modulation period, which tells us that the 3-minute waves which we are studying in the corona is owes their origin to the photospheric 3 minutes. So that means the same 3 minute is propagating from photosphere to the corona, and the solar atmosphere is coupled. So we have 3 minutes present at each atmospheric height. Now now these are slow magnetoacoustic waves. So to determine the speed of these light, we applied correlation analysis over these filtered light curve and determine the lag. We know the distance between these pass bands, and we determine the speed of these waves, and the speed was less than the speed which we expect at that atmospheric height. So we know that from the photosphere to the corona, we are studying 3-minute slow magnetoacoustic waves. Now, apart from amplitude modulation, we did frequency modulation also, and extracted the frequency modulation and determined the period of frequency modulation, and cross-correlated the amplitude frequency modulation as well, and determined the correlation was significant in amplitude modulation as well. So this means that the whole solar atmosphere is coupled. So this work has been published. So in this work, what we did is, to summarize this work, we utilized 3-minute oscillation to trace the fan loop location along with their cross-section area along the solar atmosphere, and further benchmarked our result with amplitude and frequency modulation. So this work highlights 3-minute waves in the coronal fan loop owe their origin to the photospheric 3-minute, and the whole umbra solar atmosphere is coupled. Now, since we have determined the loop location and loop cross section, and the waves propagation of these wave along these loops, and while propagating, these waves show signature of damping as well. So now I will be discussing about the damping of these waves. Now we have the area divergence. So previously we didn't know the area of the loop in the lower solar atmosphere. So lower solar atmosphere for me means layers which are below the corona. Now we have the cross-section area or the area divergence of the loop. So we need to explore. So when we study the damping of these waves along this loop, will the area divergence affect the amount of wave energy flux which are propagating along the loop? So the answer to this question is yes, they will. But whether that is a real damping or not is a question. So these area divergence does not contribute to the damping of these waves, because the energy which is generated at the photosphere when it is propagating along these loops, the energy gets redistributed along these loops, which is basically a geometric effect. Here this is a schematic diagram of a loop expansion. So whatever energy is being generated here, these energy gets redistributed along these loops. So that is not a real damping, it is just a geometric effect. So that is a very important factor which needs to be incorporated when we are studying the damping of these waves from photosphere to the corona. So the damping of these waves depends upon various factors like the frequency, area divergence, and gravitational stratifications. So all these parameters have been studied in these papers. Damping of these now, since we have the loop location and loop cross section in the lower atmosphere, we can determine the Fourier power spectrum at each location of the loop. So here we can, in this Fourier power spectrum, we can clearly see that there is a 3 minute present at the photosphere. There is a significant amount of 5 minutes and significant amount of 3 minutes. And apart from that, we have 5 minutes also present at the photosphere. Then as we move up in the temperature minimum region, the 5 minute has been cut off and 3 minute is present. Apart from 3 minutes, there is 1.5 minute also present. So we have three frequencies in the solar atmosphere: 5 minute, 3 minute, and 1.5 minute. So these are these are shaded in green, blue, and red colors. So what we did, so we now have these frequency bands. We apply band pass filter over these period bands and determine a filter light curve and divide it with a background and determine the normalized relative intensity oscillation and velocity oscillation at each atmospheric height. So here we can clearly see that clearly see clean oscillation patterns of various frequencies. So we know that this is coming from HMI continuum, which depicts photosphere. AI 1700 angstrom depicts the temperature minimum region, but we don't know the exact formation height of these pass bands. So to determine the exact formation height of these pass bands, we use the Fontella sunspot model. This line is from the Fontella sunspot model, and now we know that the temperature at which these passband contribution is maximum. So so we've overplotted this those temperature at over this Fontella model, and from here we can determine the formation height of these passband, and simultaneously at these formation heights we can determine the density at that location. So now we have density, we have temperature, so we can determine the speed of sound. So now previously we see the relative amplitude oscillation at each atmospheric height. Now we determine the absolute relative amplitude at each atmospheric height. So these are the formation height. We have plotted these absolute amplitude from the previous plot, extracted from the previous plot, and here we can see that the amplitude have increased in the chromosphere. So this is basically what is gravitational stratification or shock formation, or the umbral flashes we see in the chromosphere. Now, as I said that 1.5 minute was not present in the photosphere. So this is connected by a dashed line, and since we don't have 5 minutes at the layers above the photosphere, so again these points are connected with dashed line, which says that these are unreliable points which are connected with these dashed line. So I will be focusing more on the 3 minute waves. Now from the relative amplitude, we can, using a scaling method, we can determine the velocity amplitude as well. Now we have velocity, amplitude, we have density, and we have speed of sound. So we can determine the wave energy flux. So to calculate the wave energy flux, we are using this formula, and we see that the wave energy flux is decreasing uh, along the solar atmosphere with height. So we fitted an exponentially decaying function over this energy flux, and we determine the damping length of these waves. So the damping length of 3 minutes is around 208, and the damping length of 1.5 minutes is around 171 kilometer. So this shows frequency dependence. So basically, this shows that 3-minute waves propagate to a longer distance compared to the 1.5-minute period waves. So we did this analysis on the on this maximum correlated pixel, or the center of the contour which I showed previously, and over the whole contour, 95% contour, and we found that the energy flux was same. So that means the energy is equally distributed in the loop. Now, so this is the apparent damping of these waves, because we have not incorporated the area divergence. Now the area divergence, to incorporate the area divergence, we multiplied the area which we have determined previously with this energy flux, and we determined the actual damping of these waves. So this here is the total wave energy content along the loop. So here we see that the period of the 3 minute have increased from 208 to 303 kilometer. To 303 kilometer. This means that the increase in this damping length depicts that the waves which we were previously seeing was apparently damped, and when the area divergence have been incorporated, the damping length have increased, which means they are not damping that fast, but the damping was due to a significant amount of damping was due to this area divergence, in which the energy was basically getting redistributed in the loop. So this is the first report on the actual damping of slow magnetoacoustic wave propagating along the loop from the photosphere to the corona. So this work has been published in MNRS. So to summarize my talk, what we have done is we have developed a novel technique using a 3-minute slow wave to identify the photospheric footpoint of the coronal loop via transition region and chromosphere. So previously, these loops were not identified in the lower atmosphere. So from this technique, we can trace the loop from the corona to the photosphere. And additionally, this technique provides us the cross-section area of these flux tube at different atmospheric height, which reveals or which gives the evidence of area divergence of these loop, which is as per the theory of flux tube expansion with height. Then further, we determine the amplitude and the frequency modulation of these 3-minute waves were utilized to determine the source region of these observed slow wave in corona and the photos. In the corona at the photosphere. So these modulation are basically the property of the driver. Since the amplitude modulation and frequency modulation period, as well as when we correlated it, we found a significant amount of correlation of these amplitude and frequency modulation was also significant. We can say that the 3-minute slow magnetoacoustic waves, which are very well studied in the corona, owe their origin to the photospheric 3-minute oscillations. So this determines that the whole umbral solar atmosphere is coupled. Now, since we have studied the propagation of these waves from the photosphere to the corona, these waves show signature of damping as well. And uh, we and which shows that there is a significant amount of damping due to the area divergence. So after incorporating the area divergence on this apparent damping, we determined that a significant amount of energy is not basically lost by the wave, but it is just getting redistributed, which is a geometric effect. So after incorporating the area divergence effect, we determine the actual damping of waves from photosphere to the corona along these isolated resolved individual loops. So this approach provides us insight about the waveguide in which these waves are propagating, and this demonstrates the coupling of the solar atmosphere. So, as I said, that to study the coronal heating problem, which is one of the long-standing problem in the solar atmosphere, it is very important to see, to understand the coupling of the solar atmosphere. And from the previous images, we clearly saw that the dynamics of the each layer of the solar atmosphere is very different, and visually also they are very different. So that is why the coupling of the solar atmosphere is a very challenging task. So in our work, we have established the coupling of the solar atmosphere, which plays a very important role in understanding the coronal heating problem, or as we now call it, the atmospheric heating problem, because not only the corona is at higher temperature compared to the photosphere, but the chromosphere is also at a high temperature compared to the photosphere. So this is basically a atmospheric heating problem. And additionally now, people have started incorporating the lower solar atmosphere to understand this coronal heating problem. So that is why the coupling of the solar atmosphere is very important. So the broader implication of this work is that when we study the waves, all the MHD waves which are generated at the photosphere, they are propagating along the same waveguide. So if we know the structure of the waveguide, we can very well know that how these MHD wave will be affected by the structure of the waveguide. Like as I previously said, that a significant amount of energy is getting redistributed. So it will not be the case only for the slow wave, but the energy will be redistributed along the loop for all the MHD waves. So that is why we must know how our waveguide is behaving and what is the structure of our waveguide in which these waves are propagating. So thank you.
Thank you, Ananya, for such a nice presentation. So now we are open for questions. So if you have question, you can raise hand or you can ask your questions. Okay, Biswanath is here. He has a raised hand, so you can unmute yourself and ask your question.
There are few questions in the chat as well,
Yes,
starting
so
from
I was waiting
Shivam.
for the raise hand.
Yeah.
If he's here, if Biswanath is here, if he want to ask question. Otherwise, I'll read the questions from the chat box. Okay, so there is a question from Shivam Parasha. Which density is this? Electrons or ions?
So this is the mass density, which is the sum of the electron density and uh, sum of electron density and the ion density into mass of proton. So this is
Okay.
the so what density I was showing was basically the mass density.
Okay, so there is a question from Akash Gupta. As waves are propagating from photosphere to chromosphere and corona, density decreases. So how waves are being reflected back?
When the waves are propagating, they encounter a region of a sharp change in density and temperature. So there is a sudden shoot up of temperature and the decrease in density. So suddenly the density and temperature parameters changes, due to which when these waves encounter obstructions, a certain amount of these wave gets reflected back.
Okay, next question from Arpit Kumar Srivastav. That is, apart from supergranular motions arising from turbulent convection, how do the P modes affect or play any role in the generation of these waves?
So the generation of these waves, so there are two proposed mechanisms. So one is that the P modes is getting absorbed and and these are converting into 3-minute waves, and the other mechanism is the magnetoconvection mechanism. So it is said that the 5-minute is not playing any role, so there is already 3-minute present in the umbral dot region, and these waves are, and which are the anchor points of these loop foot points at the photosphere, and 3 minutes are being generated from the photosphere there to and then these 3 minutes are propagating to the corona. Apart from that, if you are asking that whether there is a connection between 3-minute and 5-minute, we try to explore that as well, and we find that the amplitude modulation period and the frequency modulation period, one of the period was matching with the, so there was a matching period of 3-minute and 5-minute amplitude modulation and frequency modulation, and we tried to correlate these amplitude modulation and frequency modulation as well, and we find a reasonable amount of correlation between these P modes and the 3-minute. But what we got is a significant time lag was there. So we could not explain that. So we one cannot say that whether they are connected or not.
Okay, so in that sense, we cannot say that there is any role of generation of this 3-minute magnetoacoustic wave and the P mode.
Yeah,
right?
so we cannot say that. Yeah.
Okay, so next question is from Arpit, which is what is the reason of presence of 1.5-minute oscillations? Is there any relation to driving or generation mechanism?
So yes, 1.5-minute have been seen recently, like in 2018, it was seen that it is present at each atmospheric height. However, the generation mechanism is still not known, but Yuan, a paper by Yuan, they have said that these 1.5-minute are coming from the location of the light bridge, but still we don't know what is the driving mechanism of these 1.5-minute oscillation in the corona.
Okay, so next question is from Sandeep Dubey. The question is, did you observe the effect of chromospheric resonant cavity in propagation of these slow waves from photosphere to corona?
So yes, we see that the waves, the 5-minute waves are being cut off. So this is basically the resonant frequency cutoff or the atmospheric cutoff. So the frequency of the resonant cavity cutoff is also around 4 minutes. So since 5 minutes cannot propagate up into the solar atmosphere, so yes, there can be a signature of resonant cavity while these waves are propagating. But the concept of resonant cavity is still a topic of research right now.
Yeah. So next question from Sandeep is, did you observe mode conversion from slow to fast mode during propagation of these slow waves during propagation?
So at a certain point, we see that the speed might be slightly increased, but we cannot clearly we cannot definitely say that there is a mode conversion of that, because we cannot resolve that whether it was fast or not. So what we see from the speeds is that we are studying only the slow wave. So mostly the signature of slow wave was only there, but fast mode was, we suspect that it might be there, but we cannot see a clear signature of the fast wave.
Okay, so one question from me. So as we till now, what is the maximum speed of these waves, we can say?
So these slow waves, since these when we call them slow wave, we say that these waves have the speed less than the speed of sound. So according to me, the maximum speed which a slow wave can attain is around the speed of sound. Maximum it can go to the speed of sound.
Okay, so question from Biswanath is that why do we see different locations for the points of different layers?
When we see the different location of these foot point, because the loop, as we can see, these fan loops are moving like in the coronal image, these are moving like this. So in the corona also there is, so in the umbra, again there is a certain inclination. So that is why the loop foot point is shifted towards the umbra. So I can show you an image. So this here, here we can see that all the loop, so this red asterisk symbol represents the loop foot point in corona, and this circle represents the loop location at the photosphere. So here we can clearly see that loops are moving into the umbra. So there is basically a certain inclination effect due to which the loop foot point are shifting in our correlation images.
Okay, so next question is from Bablu Mandal. Did you observe any signature of interaction in XT plot between transition region downflows or any downflow in the solar atmosphere and 3-minute slow magnetoacoustic waves above the umbra?
So flows, I have not seen any kind of flows. Because it is very well established that when we study these waves in these sunspot fan loops, these are slow magnetoacoustic waves, because the speed of these waves vary with the temperature. So that is why we say that these are slow magnetoacoustic wave and not flows which we are studying. So flow part I don't know basically. So what I know that we are studying the slow magnetoacoustic waves.
Okay, Pradeep Kumar Kashyap has raised hand. So if you're okay, you can ask your question.
Hello, am I audible?
Yes, you are.
Yes.
Okay, you have mentioned 3 periods at the photosphere, right?
Yes. 2 periods at the photosphere, 5 minute and 3 minute. 1.5 minute is in the temperature minimum region.
Okay, fine. So photosphere has only 2 periods, 3 minute and 5 minute, right?
Yes, 1.5 can be there, but due to the temporal cadence, which is around 45 seconds, so we cannot resolve 1.5 minute there.
Okay, but if I assume that 3 minute, 5 minute is there, so these are the only 2 period, or there might be other periods also? in between?
There can be other periods. So these periods are basically depicts the granulation time scale. So it is said that the granulation time scale varies from 1 minute to 10 minutes. So there can be period from 1 minute to 10 minutes. 1 minute to 10 minutes, but mainly the granulation time scale is around 3 to 5 minutes. So that is why we see dominating 3 and 5
So
minutes.
granulation is the main source of their origin, or is there any other method also?
It is said that the granulation is the main source of their origin. It can be magnetoconvection or basically P modes which are entering from which are generated by this granulation and entering the photosphere, and they are getting converted into 3 minutes. So
The
we don't
P
know the
mode-
answer.
P
Yeah.
mode can generate 3 minutes at the photosphere or not?
So that is a question of debate till now, because we don't know the exact generation mechanism of these waves, because we cannot pinpoint the location at which we cannot resolve the location of these loops or the we are, so as I said that we were stuck at 1 pixel. So if we could have a better resolution, we would have determined the generation mechanism, but till now it is still a topic of debate.
Okay, fine. So one more question, that you studied the propagation, right?
Yes.
So did you observe standing waves also between photosphere and chromosphere?
No, we didn't
So that
observe it because
if I'm not wrong, that propagation is investigated based on the phase difference, right? Or,
yes.
so you didn't get any zero phase difference for any wave
No.
period?
No. So we didn't get any zero phase difference. That is why we are saying, so that is why we are saying that we are studying the 3 minute slow propagating waves. So these waves are propagating from the photosphere to the ground.
Okay. You have also estimated the wave's energy, correct?
Yes.
So what kind of approximations you have considered there?
So we have estimated the wave energy around 10 to the power 7 Earths per
No, that
centimeter
is fine.
square.
This is the number you're saying. What I'm asking, when you're calculating the wave energy, you have to consider some approximations because you're using observations, right?
Yes.
So what kind of approximations you have considered there?
Basically we have determined the velocity amplitude, which is the most important parameter in
Let me rephrase my question. What kind of a structure you have taken to calculate?
So we have traced these loop and we have taken that structure, only the structure of the waveguide.
Structure of the waveguide. Okay.
So the loop tracing which I showed, we are saying that this is the waveguide which along which the waves are propagating.
You mean expanding flux tube, right?
Yes, expanding flux tubes.
One last question. You have mentioned in your conclusion that you provided novel technique to estimate, to detect the foot point of loops in the transition region and chromosphere, right?
Yes.
But as far as I know that using the intensity contrast, we can find out the foot point of the loops. For example, if you're talking about 3 minutes, 3 minutes is also visible in the quiet sun, right? So I don't know. I just want to know what kind of novelty you have introduced there. Because if I have to check the foot point of the loop in the chromosphere and transition region, so I can at least in the transition region, I can use this intensity contrast there, right?
But in the umbra, we cannot see these loops. So
in the transition region.
In the transition region also, when I show this image, so in this image, we can clearly see that these points, I have plotted these points as the loop points, but here we can clearly see that loops are not clearly visible. We cannot say that this is the location of the loop.
Well, coronal loops are not visible in lower solar atmosphere. There are other
Yes.
category of the loops, let us call the cool loops, and that was discovered by IRIS itself. I mean, they were there, but because IRIS is having good resolution, so in their observation, those cool loops are clearly visible. But the coronal loops, because they're bigger loops, they're having bigger curvature, so you cannot see the loop structure at the photosphere or chromosphere. You can see only their foot point, and that is in the dark region.
So yes, that is what I'm saying, that we don't know the exact location. We know that they are coming from the umbra, but we cannot pinpoint the location of these
You are
loops in the
saying
lower
that
solar
you
atmosphere.
are saying that you will take one loop at the corona, and then you will exactly tells the route of that particular loop in the transition region or chromosphere.
Yes, yes. So this is the technique which we have devised to determine the loop location and the cross section at each atmospheric height.
Yeah, but you said it is based on the 3 minutes, right?
Yes, it is
For
based on
example,
the 2 minute.
for example, if I take two different loops and
Yes.
I'm tracking their chromosphere and transition region counterpart, both counterparts are showing 3 minutes.
Yes.
So how will you differentiate this is the root of first loop and this is the root of second loop?
So, the amplitude modulation, when we determine.
Sorry, I joined your talk little late, so that is why I'm asking, because I skipped the
Okay.
first part.
Okay, so to benchmark these results, what we did is we determined the amplitude modulation and frequency modulation of these 3 minutes as well. Now, the amplitude modulation and the frequency modulation are basically the property of the driver. Now, which is driving these waves. So since the amplitude modulation and the frequency modulation was showing a same period, and they were also very well correlated at each atmospheric height, so this confirmed that the propagation, that the 3 minute is propagating along these loop structures only. And when we check the amplitude modulation at a surrounding pixel, we find that the amplitude modulation was not correlated. So using the amplitude modulation and frequency modulation, we further benchmarked our technique of this 3 minute oscillation.
So you're saying that this amplitude modulation is the base to track the root of particular loop.
No, I'm saying that 3 minute oscillations can be used to track these.
That's
We
what
use
I'm
3
asking.
minute, but we use 3 minute, but to benchmark further this result, we use 3 minute amplitude and frequency modulation.
Okay.
So this can be done with 3 minute. If we want to do with amplitude modulation also, we will be getting the same result.
Oh, okay. So just one last question. So you have said that you find out the real dissipation, not the geometric effect, right?
Yes.
So do you know which physical process is responsible for that dissipation?
So there are various physical processes like conduction,
No, but do you
like
quantify in your?
no.
Okay.
In our work we haven't quantified.
Okay.
So you are asking about non-ideal damping mechanism, and I have focused only on the ideal damping mechanism, which are basically gravitation stratification and the area divergence.
Okay, fine. Thank you. Thank you very much.
Okay, any other question? If not, then we can thank the speaker again. Thank you for such a nice presentation.
Thank you all for attending.
Thank you. So okay, we can leave the meeting now. Thank you.
Yeah, Pooja, you can stop the recording now.
Yeah.
Yeah. Thank you, Pooja. Thank you, Ananya.
Thank you.